Hi, I'm Michael T. Irapta from BSCE 4B. Last lesson, Mark Louie Ubani explained to you about flow nets. So, I'm gonna talk about boundary condition. First, what is a boundary condition? Boundary condition are constraints necessary for the solution of a boundary value problem. Both ordinary and partial differential equation needs boundary condition to be solved. Different types of boundary condition can be imposed on the boundary of the domain, say D. The choice of the boundary condition is fundamental for the resolution of the computation problem. A bad imposition of the boundary condition may lead to the divergence of the solution or convergence to a wrong solution. There are 5 types of boundary condition. First is the Dirichlet boundary condition. Second, Newman boundary condition. Third, Robbins boundary condition. Fourth is mixed boundary condition. And the last one is Cauchy boundary condition. First, I'm gonna talk about the Dirichlet boundary condition. Dirichlet boundary condition is a type of boundary condition named after Peter Gustav Lejeune Dirichlet. This condition specifies the value that the unknown function needs to take on along the boundary of the domain D. Example, if u of x, t represents displacement of vibrating string and its end are fixed at x equals to 0 and x equals to h, then the condition of u of 0, t is equals to 0 and u of h, t is equals to 0 are Dirichlet boundary condition. Next is the Newman boundary condition. The Newman boundary condition is a type of boundary condition named Carl Newman. This condition specifies the value that the derivatives of a solution is going to take in the direction normal to the boundary domain capital D, which is written as partial u over partial n. The normal derivatives on the boundary partial u over partial n is defined as partial u over partial n minus equals the gradient u, the period n is equals to partial u over partial x sub 1, comma, partial u over partial x, partial x2, comma, 2 partial u over partial x to the n term of n, where n is the outward normal boundary. Newman boundary condition example. Suppose u of x, t is the temperature in a rod of length capital L if the rod is perfectly insulated at x equals to 0 and x equals to L. The heat flux at this point is 0 from the Fourier law of heat conduction. It follows that the partial u over partial n of u of 0, t is equals to 0 and n is equals to partial u over partial x sub 1 of capital L, t is equals to 0. These are the Newman boundary condition. Next one, or the third one, is the Robbins boundary condition. Robbins boundary condition is a type of boundary condition named after Victor Gustav Robin. The Robbins boundary condition is weighted combination of Dirichlet boundary condition and Newman boundary condition is all the parts of the boundary. The general part of such boundary condition is alpha u plus beta of partial u over partial n multiplied to the boundary equals to f of x of partial or the boundary, where constant is the alpha and beta represent weights. Robin's boundary condition example. Suppose U of x comma t is the temperature in a rod of length I. If the rod is poorly insulated at the end of the rod, then the boundary condition might take the form U of 0 comma t plus partial U over partial x of 0 comma t is equals to 0, and U of capital L comma t plus partial U over partial x of capital L comma t is equals to 0. So this is the boundary condition. Mixed boundary condition, or the fourth one. Mixed boundary condition refers to the case in which Dirichlet boundary condition are prescribed in some of the boundary while Newman boundary condition exist in the other. Suppose of U of x comma t is the temperature in a rod of length L, capital L. Let one end of the rod is in a water bath with constant heat transfer rate, then mixed boundary condition take the form U of 0 comma t is equals to A, and partial U over partial x of capital L comma t is equals to B, where our A and B are constant. Let's go to the last one, which is the Cauchy boundary condition. Cauchy boundary condition is a type of boundary condition named after Agustin Louis Cauchy. The Cauchy boundary condition specifies both the functional value and normal derivatives on the boundary of the domain. It differs from Robin's condition because the Cauchy condition implies the imposition of two constraints, or one Dirichlet B period C plus one Newman B period C is the Robin's boundary condition implies only one constraint on the linear combination of the unknown function and its derivative. Next is the Cauchy types of boundary condition example. Cauchy boundary conditions are less common, but they are ideally imposed on a problem to ensure that a unique solution exists for heat equation, or partial U over partial t equals to partial 2U over partial x2. The condition is U is equals to 0 comma t, and partial U over partial x of 0 comma t is equals to B, our Cauchy boundary condition. Let's take a look in our example. We want to find a solution to the given BVP problem of the second derivative of y with respect to x minus y is equals to 0. Y of 0 is equals to 0, y sub 1 equals to 1. If we know that y of x is equals to c sub 1 times e to the x plus c sub 2 times e to the negative x is a general solution to the differential equation. So, given a general equation here, we want to find, and these two condition, we want to find a particular solution. So we have y is equals to y of 0 is equals to 0. And if we substitute 0 for x which is here, the function must be 0. So c sub 1 is to 0 plus c sub 2 times e to 0. So that must be equal to 0. Remember that e to the power of 0 is equals to 1. So C sub 1 is equals C sub 1 plus C sub 2 is equals to 0. So which means C sub 1 is equals to negative C sub 2 or vice versa, so they're opposite of one another. So we're going to keep track of this. Now we'll use the fact we know that y of 1 is equals to 1. So we have y of 1 equals to 1. So we're gonna have c sub 1 times e to the power of 1 plus c sub 2 times e to the negative 1. So that must be equal to 1. Again, we're trying to find the value of c sub 1 and c sub 2. Notice that this equation still have two unknowns, but we do know that c sub 1 is equals to the negative c sub 2. So let's form up substitutions here of c sub 1 by replacing negative c sub 2. So negative c sub 2 e plus c sub 2 e to the negative 1 is equals to e negative 1 equals to 1. So let's go ahead and factor out our common factor of c sub 2. So that's going to leave us negative e and negative e sub 1. So I'm going to write out e to the power of negative 1 minus e is equals to 1. So we're gonna divide by this to cancel. So we know that c sub cancel na tandaya, c sub 2 is equals to 1, e sub 1 negative 1 is negative 1 minus e. And since we know that our c sub 1 and c sub 2 are opposite, we also know that c sub 1 is equals to negative 1 all over e to the negative 1 minus e. Remember that this all the information we need to solve this BVP problem. So we now know the c sub 1 and the c sub 2. Thank you for listening.